So we talked about transformations for rotations, transformations for translation. The Denavit-Hartenberg convention consists of 4 transformations. A was the matrix which describes these transformations. 3A I to I minus 1 equals rotation about z-axis by an angle theta I, translation about z-axis by d, then translation about x-axis about ai, and then rotation about x-axis by an angle alpha I. Okay, so if you look at the formulas for these rotation, then translations, this is going back, then just a copy paste from there, c theta I minus s theta I. Okay, so these 4 multiplications, which you clearly don't want to do by hand, use MATLAB instead, can be, you can do these multiplications to get this formula, and you'll probably see this formula only, well, you'll never compute this yourself. You'll always, I hope, use MATLAB now that you know how to use MATLAB symbolic stuff. I've shown that in the first class. Where c theta I is cosine theta, s theta I is sine of theta I, c alpha I is cosine of alpha I, s alpha I equals sine of alpha I. Okay, now when we talked about rotations of an object, I told you there's a rotation matrix has 9 numbers, but there are 6 constraints, which means that you only require 3 numbers to describe rotations. Really, it boils down to 3 angles: rotation about x, y, z, x, y, x, and so on. So there are like 12 combinations. if you want to represent rotations as well as translations, then you need 3 numbers for rotations, like I just described, and you need 3 numbers for translation, because an object has its location, which is an x, y, z, and then of course the rotation. So 6 numbers are required to describe a rigid object in space. However, we've seen that the Denavit-Hartenberg convention here has only 4 numbers to describe the object completely. The 4 numbers are given by the 4 transformation: theta I, di, ai, and alpha. Okay, so there is like a inconsistency here. For rigid body rotations and translation, you need 6 numbers, but DH convention tells you only require 4 numbers. So why don't we require 6 numbers to describe the position of a link? It turns out that you can do this, that is reduced from 6 to 4 numbers, because the DH convention uses this very special way in which you define how links or this axis are connected, and that helps you to reduce numbers from 6 to 4. So let me put that down. So normally one needs 6 numbers, 3 translation plus 3 rotations to describe a rigid body, but DH, that's going to be our shorthand for Denavit-Hartenberg convention, uses only 4. Okay, the question is why, and that's because of a special way in which these axes are defined. So as I said, if there are 6, remember there were 9 numbers for rotation, which is 6 constraints, that reduces the rotation matrix. That is, you need only 3 numbers to describe the rotation, because it's 9 minus 6 conditions, 3. In this case, there are 6 numbers actually for rigid body, but since there are 2 conditions, those are 2 constraints, and so you reduce the number of parameters you need from 6 to 4. So those 2 conditions are one is axis xi is perpendicular to zi minus 1. So remember, we are talking about axis fixed to each link. So axis 0, 1, 2, 3. And so when I say xi, it really means one of those axes, and zi is the axis preceding it. So when they are perpendicular, that's one condition which we'll enforce. And the second condition is axis xi intersects the axis zi minus 1. So those 2 conditions lead to 6 minus 2, which is equal to 4. That's why we have 4 numbers and not 6 numbers, which describe the the position of a link. There's a derivation on how this 6 reduced to 4. I will not go through that, but the reference is, if you want to understand this, the reference is book by Spong, which is one of the reference book. It's on page 78. Okay, we will be good users of this convention. We will not start proving things or showing any of these things. Okay, so if you want to know more, that's it. Yeah. Yeah.
So what's the difference actually between the 2 conditions? I mean, xi is perpendicular to zi.
Yeah.
That means it has to intersect.
No. So if you have, so it's perpendicular and intersects. So if the axes are away, then they don't intersect. So 2 different things. Okay, so this is probably the hardest part of the course, which is how do you assign coordinate frames and how do you use that to describe the kinematics. And once we describe the kinematics, we'll see we can do animation, right? Just like the animation we did for the differential drive car. So here are the steps, and really the good thing is that since the take-home exam, you don't have to remember this. You can just go back and refer to this. Copy pasted it here. Essentially, you'll be given a manipulator and you'll be told there's one rotation joint this way, there's another rotation joint this way, there's another rotation joint this way, so 3 links. How do you describe the kinematics of this? So it's called forward kinematics because in forward kinematics you describe the angles of the joints and then you're able to describe the complete representation of the manipulator. The other problem which we'll also do is we are only given the position of the end effector, where the end effector is x, y, z, and we'll be figuring out what the angles are, which will give us that particular theta. But we cannot do that calculation, what's called the inverse kinematics, unless we do the forward kinematics, which is the subject of today's lecture. Okay, so 3 steps, 1, 2, and 3. The first step is assigning coordinate frames. So I'm reading from the handout. The second is generating the table. Those are the 2 hard steps. The third one, apply the DH formula, is really very simple. You can go to number 3 in the next page, just to apply the formula, which you can see the same formula I wrote down, AI with respect to frame I minus 1, and that theta I, di, alpha I comes from the table 2, which will be generated. So our goal is to generate this table 2 on step 2. And in order to generate the table, we have to do a bunch of things. Okay, so the best way to illustrate DH is to start with simple examples. The simplest example I can think of is a 2-link manipulator, what is also known as a double pendulum. So we'll do a double pendulum. We'll see how to apply this, and we'll go from there. Okay, so instead of trying to explain to you, I think the key step is in number 1 is step number 3, where there is different cases. Instead of trying to explain what that means, I'll just explain to you in examples. So we'll do a problem, we'll see how those things are used. So here is the first problem. Let's call that problem 1, forward kinematics of 2-link manipulator. Okay. Okay, so 2-link manipulator example will be my hand. So 1 link, 2nd link, ignore the wrist for a moment, and it's only planar. It only moves in the planar direction. So you can rotate about this axis. That would be the elbow joint, and then this is the shoulder joint. Okay, so it's all planar. Axes are pointing in this case the z direction. So it's 2-link. Call it planar manipulator. So the degrees of freedom are, so degrees of freedom is a terminology which is used to describe how many independent numbers are required to describe the motion. So in this case, well, if it's a single pendulum, it's theta, only 1 degree of freedom. If it's a manipulator, it has 2 joints, so it's 2 degrees of freedom. 3-link would have 3, and so on. So 2 degree of, this is a 2 degrees of freedom manipulator. The degrees of freedom are theta 1, theta 2. I also need to give you the dimensions. So let's call this link as L1, the other link as L2. Okay, the question is, derive the forward kinematics of the two link manipulator shown. Okay, so let's use this recipe. Okay, start from 1, we go all the way to 3. I'm going to redraw it so that we can start off afresh. Okay, all set. So I'm going through this first page. So the first step is assign zi along axis of actuation. Do this for each link. Zi is always going to be the axis about which the system rotates. So if this joint rotates about, it's rotating this way. So clearly this is the axis of rotation. Same for this one. Let's say that my wrist is rotating this way. Then my axis of rotation is going to be that, because that if I curl my finger, well, if I point my thumb in the direction of the motion, then the rest of my fingers gives me the direction of motion. Okay, for a prismatic joint which translate like this, that's going to be the degrees of actuation. So it says the first step says assign zi along axis of actuation. Now in this case, the axis of actuation, since it's planar, the axis of actuation is in the z direction, which points out. Okay, so this is really hard for me to show, but let me just make an attempt. That's going to be z0, and then c1. This is out of plane. You do not have to show this normally because it's understood it's out of plane. If it is out, if it is a planar figure, then you don't have to show it. But I'll just show that. So zi along axis of actuation. Do this for each link. Number 1 is done. Number 2, assign the base frame OO, XO, YO, ZO. We have already assigned Z0 in earlier steps, so we've already assigned Z0. Choose X0 orbital. In this case, I've already assigned X0, Y0, Z0, so we can skip that, but in the next problem, I'll show you how to assign that too. So the base frame is attached, so 0 is the base frame. Okay, next, number 3. Now assign OI, XI, YI, ZI. So this is going for each link. ZI is already attached. So in this case, I equals 1. Since we already finished base frame, which is 0. We attach XI based on the relation between ZI minus 1 and ZI. So for X1, so we need to attach X1 based on the relation between ZI minus 1 and ZI. So I is 1, so the relation between Z0 and Z1. So we are now going to attach X1 based on the relation between Z0 and Z1. Okay, Z0 is this, Z1 is that. There are 3 cases for Z0 and Z1, so we need to find the relation between them. Zi minus 1 and Zi are not coplanar. Okay, this is probably the hardest one. They are not in one plane, they're in a different plane. Clearly they're in one plane here. Right? They're in the same plane. Zi minus 1 is parallel to Zi. So Z0 is parallel to Z1, and that's true, right? Z1 points out, Z0 points out, so they're planar. Sorry, they're parallel. When they are parallel, we got to follow the whatever is set here. So in this case, there are infinitely many perpendiculars between Z0 and Z1. You agree? If there are two parallel lines, you can draw multiple perpendiculars. In order to make our life easy, what we do is choose xi is chosen so that it passes through OI. So x1 is chosen so it passes through O1. Okay, so in this case, so between this, there are multiple perpendiculars like this. The suggestion is you want to choose x1 such that it passes through to make the question simple, choose OI so that xi passes through OI minus 1. So x1 passes through OO. Okay. So I'm reading off this part. Says that xi, so x1 passes through O, I is 1, so O0. So what we do is we essentially draw x1 so that it passes through O. Okay, and then you don't have to read that, but it will be clear when we do the table. So we're done with attaching x1. Now we move to attach x2. Okay, x2 is again we ask the question. Where are we done? Oh, so we are done with, well, we're done with, there's only 1 and 2. So we're done with both links. So x2 is basically the end effector. End effector is the final link where this is the link where you attach the tool or which will do some work. So in this case, we're not going up to the end effector. For end effector, there's number 3. So end effector is here. So we have not reached there yet. So let's see if we exhausted all of them. Well, we have exhausted all the links, all the degrees of freedom. So we now have to move to the end effector. So I'm reading off the end effector. Finally, we need to find the position and orientation of the frame n, so the end effector. There is the tool. This is where the tool will be attached. As I said, choose Zn. So Zn now is the end effector. In this case, it's going to be 2. Choose Z2 to be the same as Zn minus 1. So Z2 should be the same direction as Zn minus 1. So Z1. So our Z2 is also going to be out of the plane of the paper like this. Okay, now once you've attached Z2, we have to attach X2. Okay, it's always you first attach Z, then attach X, and then you do Y. So again, we need to find the relation between Z1 and Z2. You can see that Z1 is parallel to Z2 because both of them come point out of the axis of the plane of the paper, and so there are infinitely many perpendiculars. To make your life simple, what you want to do is you want to attach X1, X2 such that it passes through OI minus 1, which is O1. So this is x2. Okay. In fact, this is theta. This is theta 2. And the last thing is attach y-axis. We've already attached x and z for each of the links. The way you attach the y-axis is you just use the right-hand rule. So x, y0 is attached. It's already there. If you want to attach y1, so x1 is pointing that way, z comes out of the plane of the paper. So if you want to attach a y, it's going to be z cross x is y, so y has to be at right angles this way. In fact, if you do x cross y, your thumb gives you the direction of z1. So z1 points out of the plane, so y has to be planar at 90 degrees to x1. Similarly, x2, y2 is here. So that's the frame. So first thing is attach frames. The next step is to generate the table. I'm going to step 2 now. We'll copy this. We'll eliminate things which are not useful, which is this axis, where they point out of the plane of the paper. Okay, so next is the DH table. The table will always look like this. Link AI, alpha I, DI, theta I. Since there are two links, I'm going to put 1 and 2. So we need to populate this table with numbers. So 8 numbers are needed. Each link has 4 numbers. Okay, so this is a, well, I like to do it this way. This is a sort of a easy way of doing it. I wrote it down here. AI, alpha, how do you get that? I like to draw this figure. Xi, Ci minus 1, Ci alpha I, and then the other figure is, and this figure will help me to quickly fill this table. Xi minus 1, Xi, Zi minus 1, theta, and then this is theta. Okay, so besides this same figure which I reproduced, I've written down what AI, alpha I, Di, theta I mean, okay? And so I'm going to use that to basically populate this table. I would need to look at this figure and then use that to populate this table. So let's start with the first element, AI. Okay, so if you read the definition for AI, it's the distance between Zi minus 1 and Zi. Okay, next to that. So if I want to find A1, it's going to be the distance between Z0 and Z1. So Z0 points out from here, Z1 points out from there, right? So we need to find the distance between those two axes, which is basically the length of this link, which we wrote down as L1. So that's going to be L1. Okay, next is alpha I, which is the angle between Z0 and Z1 along Xi. So angle between Z0 and Z1 along Xi. In this case, I is 1, right? So along X1. Okay, so if you look at this figure here, yeah, that figure, what's the angle between Z0 and Z1 along X1, which is that. So if these two lines are parallel and X1 is that way, then the angle between these two is, they're basically parallel to each other, right? So if they're on top of each other in a way, so the angle is going to be 0. Is that clear? Z0, Z1, we want to find the angle along this axis. So the angle is 0. It wouldn't have been 0 if it's a slightly skew, then it wouldn't have been 0. Since they are lined up parallel to each other, the angle is 0. Okay, next, DI. So if you read this, it's the angle between Xi minus 1 and Xi along Zi minus 1. So angle between X0 and X1 along Z0. Sorry, distance between X0 and X1 along Z0. So X1 is that way, upwards. X0 is this way. And you want to find the distance between these two axes, those two axes, along a special axis, which is axis Z0. The axis Z0 is this way. So we want to look at the distance between these two lines, but in this direction, because that's the axis. So since they start at the same point, the distance is 0. Now, if let's say this axis was that way and this axis was ahead, like this, and then you're looking at it from this angle, then this angle is not 0 now. But moment they're they start from the same origin at 0. So the distance along z0. Is that clear? Yeah.
Are they on the same plane?
What's that?
Are they on the same plane or are they on the
There, yeah, this manipulator is in the same plane. Yeah. If it was slightly offset, which is really hard to show, I don't have an example here. Yeah, like this one, I would say, not really. If there was an axis here and this is moving, then that is not 0. But we assume that both the links are in the same axis, so the same plane. That's why they are 0. So this is, so there'll be examples where that's not equal to 0. So don't worry about it. And then theta 1 is, if you read through, angle between x0 and x1 along z0. So angle between x0 and x1 along z0. So x0, x1 along z0. So if you want to go from this to this along z0 axis, then we need to turn by an angle theta 1. So that's theta 1. Okay, so it's like you do have to do this very slowly, and I would say the more you practice, the better you get it is. It's very slow to explain it, but I'm sure that if you do it in your head, it's much faster. You can do the same. The second line actually comes out to be very, the logic is very similar to the first one, so I will not explain it too much in detail, but you should convince yourself. I'll get to much harder examples. The next example is much harder, so I will just put this down here, but you got to go and check this yourself, that this is true. So this is step number 2. Okay, and then the last step, which is the most trivial step, is use that table to figure out the DH formula. So A10 is going to be C1 S1 S1 C1s. Sorry, this should be L1 C1 L1 S1. The C1 is cosine theta 1, S1 is sine theta 1, and then A21, which again comes from the DH formula, C2 S2. And if you put it all together, which is what you're after is A20. What is A20? It basically tells you what's the frame 2. Frame 2 is attached to the end effector. We want to find how the end effector moves relative to the shoulder, right? Because 2 is going to be attached to it. So if you get A20, it's the formula we've written down so many times now. This comes out to be C12 S12. This is after doing simplification. So there's a command called simplify in MATLAB. It will actually do this for you. You don't have to do anything manually. Okay, so that's what you get. Now the question is, what does this really mean? It turns out that this part describes the rotation of the end effector with respect to frame 0, and this part determines the position of the end effector with respect to 0. So in this case, we have, I'm going to draw the manipulator. Theta 1, theta 2, L2, L1. By the way, I should C12 is cosine theta 1 plus theta 2, and S12 is sine theta 1 plus theta 2. So this point, let's say it's E, that's the end effector. This is given by D20, which is L1 C1 plus L2 C12, L1 S1 plus L2 S12, and 0. Okay, you can actually use trig here to figure out that angle. This angle is the same as that angle, so it's theta 1. So the end effector is actually, so just from trig, you can find the position of the end effector from 0. It's going to be L2 cosine theta 1, sorry, L1 cosine theta 1. This part is L1 cosine, since this is L1, my bad. This is L1 sine theta 1, right? Theta 1 L, that's 90 degrees, so L1 sine theta 1. And this is going to be L2 times sine of theta 1 plus theta 2. That's complete angle. So this distance is L1 sine theta 1 plus L2 sine theta 1 plus theta 2. And if you want to find this distance, so again from trig, this much is L1 cosine theta 1, and this distance along the x-axis is L2 times cosine theta 1 plus theta 2. So L1 cosine theta 1 plus L2 cosine. Okay, and what you see here is the same thing. You got the same thing using the transformation. This is the x coordinate of E. X coordinate is L1 cosine 1, cosine theta 1, plus L2 cosine theta 1 plus theta 2. And then the y coordinate is L1 sine theta 1 plus L2 sine theta 1 plus theta 2. So you get the same answer using trig. It's fairly easy to do this for a planar geometry, but once we talk about 3 dimensions, you'll see that it is much harder to do the trig. It's much easier to do these transformations because we would use that pH formula. Okay, so real power of this is when we go to 3 dimensions. In fact, manipulators, when you have a industrial manipulator, they will have 6 joints. So there'll be 6 such transformations. When you put them all together, you'll be able to describe the forward kinematics of the manipulator. Okay, so this is the same. This thing is the same as that. Okay, any questions? Okay, so that was, I would say, by far the easiest example. We get to harder ones, and that's where to be useful. Okay, so we'll start labs. I think we'll give the kits out either Thursday, most likely Thursday. Position and orientation of the end effector manipulator shown below. Okay, now I'm going to draw the manipulator in a very funny way, but that's what convention we're going to use. We're not going to show the link length, we're only going to show the joints, okay, or the degrees of freedom. So here is my manipulator. Okay, cylinders and boxes floating in the air. Can that be a manipulator? Well, because it causes a lot of clutter to show link, we just ignore showing the links. We just show the degrees of freedom and of course all distances. So what this means is this manipulator has 3 degrees of freedom indicated by thetas and d's. Okay. If you have a cylinder, it means it's a rotary joint, revolute joint, it's a hinge joint. If it's a box, it means it's a prismatic joint. So in this case, the rotation is about theta axis. In this case, there's a translation of the box in D2 upwards, and then for the other box, it's translation D3 to the right. And the end effector is here, which means clearly there is a link. It's basically a rigid body there which connects D3 with the end effector. Okay, this is just to keep the clutter manageable. We just draw that. So, okay. Okay, so now we will start assigning coordinate frames. That's the first step. And once we assign coordinate frames, we'll fill the table for the DH. Okay, step 1. You know what? Let me redraw this. In case you're practicing, it's be good for you to have this figure without anything drawn on it. Okay, let me copy this on a new page. Okay, let's start assigning coordinate frames. Okay, you follow this. Step 1, first page, assign zi along axis of actuation. This is the simplest step, which is assign zi. So first of all, z0 would be along theta 1. So that is z0. Next is z1, which is along axis of actuation of the next link, z1. Next is z2, which is the axis of actuation of the next link, d3. And so we're done with all the links except the end effector. We keep the end effector later on. Okay, so we've assigned z. Now let's go to assigning x for each of the links. Okay, this is where we go from steps. Well, before we do that, you have to assign actually the frame 0. So step number 2. Okay, choose the base frame x0, y0, z0. So the way we do this is, it's basically you do an arbitrary choice for x0 and y0. You could choose x0 to be this way, this way, this way, this way, any way you want. But it has to be 90 degrees to z0. That's clearly the condition. So in this case, I chose x0 to be in this fashion. Okay. Again, you could have chosen it this way. Absolutely fine. So y0 is chosen such that it is 90 degrees to x and z. So z cross x gives me y. Or if you're more comfortable, if you do x cross y, you get z. So that's it. So we finished with frame 0. Now let's move on to get frame 1. So we need to attach x1 to z1, and that depends on the relation between z1 and z0. Okay, we need to figure out which of the 3, A, B, or C, would z0 and z1 belong to. So are not coplanar? That's clearly not the case. Are they parallel, or do they intersect? Okay, they actually intersect in this case. Okay, parallel is when they are that way. In this case, they intersect. And so if they intersect, then xi is chosen to be normal to the plane formed by z0 and z1. Okay, so z0 and z1 are this way. It has to be normal. So when it's normal, it can be could be this way, any way you want to. So it's really arbitrary, but it has to be 90 degrees. In this case, I decided to have x1 to be pointing this way, but you could have it that way, this way. All these angles are fine. if you wanted, you could now attach y1, which is going to be 90 degrees to, well, z cross x to give you y. So y. So we're done with frame 1. Let's move to 2. Let's attach x2. To attach x2, we need to find relation between z1 and z2. z1 is pointing upwards, z2 is pointing that way, and basically if you look through this, they are actually intersecting too here in this case. Because it passes right through, z1 passes right through z2. So if z1 and z2 intersect, then xi, which is x2, is going to be at right angles to z1 and z2. So if z1 is this way, z2 is that way. Now we only have two choices for x2. It has to be 90 degrees to both of them. So it has to be either this way or that way. It cannot be this way, because if it was this way, then it is not 90 degrees to this axis. It cannot be this way because it's not 90 degrees to that axis. So it has to be either coming out this way or going that way. So it's up to you. You want to choose it to be this way, that's fine. If you want to choose that way, that's also fine. So you have only two choices. Unlike the previous one, x1, where x1 could have been any direction, you could have put it anywhere. Okay, so I chose x2 to be this direction, but you could have totally taken it pointing inside the plane along the same axis.
How did you know you were intersecting?
Because z1 is upwards, z2 is that way, and so they intersect. This is z2, z1.
How did you know they are on the same plane?
They're in the same plane because there is no, if they were not in the same plane, I would have given you that some distance between those two. So if they were not this way and they were this way, then I would have given you this distance. I have not given you that distance, so you can assume it to be in the same plane. Okay, so this is hard to, it's 3D, so it's hard to imagine. So it's this way, but it could have been that way, and then the distance would have been. And
That's why it means you want to intersect.
then the same plane. They're again the same plane.
They're just parallel.
They're parallel, yeah. Unless you're given dimensions, you assume it to be 0. So in this case, given you d1, if I had not given, we would have presumed it to be 0. Okay. Okay, then we can assign y2, because y2 is just normal to x2 and z2. So z cross x is going to be y. So which direction is y? Is it y2? Is it upwards or it's downwards? It's downwards, right? So this way. Because x cross y, when I do x cross y, I get z. Okay, that means we've finished number 3, and we go to the end effector. The end effector, the way you attach the frame to the end effector is choose the end effector frame, in this case z3, to be the same direction as z2. So z3. And what happens is you'll see that x3 is this way, and then y3 down. Okay, so this is the major part. Next, let's go to the DH table. So now we have 3 rows, because there are 3 links, θ1, d2, and d3. Okay, and I really like to draw this, and this is really optional. Some people. So I have drawn this thing, but I don't draw that quite. I just use this sort of a mnemonic to remember that for AI alpha I need to look along axis I for the relation between zi minus 1 to zi, and then for di theta I need to look along axis zi minus 1 for a relation between axis xi minus 1 to xi. Okay, so this is something which I write down just for myself so that it's easy for me to quickly do this instead of trying to refer to this figures. It's just is easy. So you'll see how I use it, and it's up to you. You can develop your own trick to remember how to fill this. I use that thing. Okay, so here's how I do it. Let's start with these two. These two are related with that. So first is, that's a distance, that's an angle. So we need to find the, how much time? 15 minutes, that's enough time. So let's put I equals 1. I is 1. So we need to find the distance from Z0 to Z1. I put I equals 1. So distance from Z0 to Z1 along X1. Okay. So once I have that in my head, Z0 and Z1 along X1, I'll look at the figure. Z0 is upwards, Z1 is upwards. I need to find the distance between those two along X1. Where's X1? X1 is there. So the distance is 0. Okay. Next, I look at the angle between Z0 and Z1 along X1. So angle between Z1 and Z0 along X1. So if I look at it from this way along X1, what's the angle? It's simply 0. So that's 0, 2. Okay. Next, D1 theta 1. I put I equals 1. I need to look at the distance from X0 to X1 along Z0. So distance between, I keep that in my head, distance between X0 and X1 along Z0. So distance between X0, which is this, X1 along Z0, along this axis. So distance between two along that axis. It's D1. So that's D1. And then angle between X0, X1 along Z0. It's 0. Now here's the trick. It is 0 at this point of time because that's how it starts. But eventually when this manipulator spins or this rotates, it'll actually move by angle theta. So if you put 0 there, that's the way it is shown. But we want to solve for the generic position when theta is not equal to 0, right? It is 0 right now because you can see that they are lined up and theta 1 is actually 0. The moment theta turns, this will move, and so the generic angle is theta. So it would be incorrect to put 0 unless you're solving a special case. So I would put theta 1. I could have potentially drawn a rotated configuration if that was easier, but I like to do it this way because it's much simpler. In fact, you should, in every line, since it's a degree of freedom system, every line should have a degree of freedom. So that's a degree of freedom. If you do not have any degree of freedom in that line, that means that doesn't make sense because it has to have, each line corresponds to 1 degree of freedom, right? That's for the revolute one. This one should have a D2 in it, and this one should have a D3 in it. That would be wrong. Okay, let's do the second. Let's do the second link. Okay, so I put I equals 2 in the first formula. So I equals 2. So I would have the distance from Z1 and Z2, Z1 and Z2 along X2. Okay. So Z1, Z2 along X2. So Z1 is upwards, Z2 is this way. I want to find the distance between these two along this direction. X2 is that way. It's clearly 0. So next is the angle between Z1 and Z2 along X2. So angle between Z1 is this going upwards, Z2 is that way, and I want to find the angle between these two axes along X2. Okay, now it's hard, right? They are not well. In order to find the angle, what you do is, so X2 literally points out of the plane of the paper. I need to basically curl my fingers. So if I curl my fingers from, I need to curl my fingers from that to that. So Z1 is this way and Z2 is that way. So I need to curl my fingers that way. When I do, I curl them by 90 degrees. But my thumb is not along x2. X2 is this way, but thumb is along minus x2. So the angle is 90 degrees, but it's not positive, it's negative. Sorry?
If it's the parallel, we're going to be 180.
No, so Z1 is this way. Z2 is like that. Think of the vector this way. So I need to find the angle between this and this. So I need to go 90 degrees for sure. But the question is it positive 90 or negative 90? If it was positive 90, then x2 is this way, right? The angle. So if it was positive, I have to go this way. But my convention is always I go from I minus 1 to I, which is 1 to 2. So I need to go this way. My thumb is pointing against x2, so it's negative 90. Okay, this is one of the cases where it gets hard. You have to be very careful. Okay, next I put I equals 2. So I have x1, x2 along z1. So distance from x1, x2 along z1. x1 is this way, x2 is parallel upwards, and then the distance along z1. So z1 is this way. So we need to find the distance from this to this axis along this direction. So clearly that is d2. And then the angle from x1 to x2 along z1, since they are lined up parallel to each other, okay, the angle, if you have to see it this way, it's 0. If it was slightly skewed, it would end up at 0. So it is 0. Okay, and finally, okay, I'll write it down. You want to go and check. This is, by far, this was the hardest one. The last line comes out to be 0, 0, D3, 0. And so I want you to go and check this is true. Okay, convince yourself this is true. I skipped this because it's fairly, I don't think there's much interesting dynamics here. There's interesting here, right? So I just skip. Do it slowly, and the more you practice, the better you get. So once you have this, all is left is to copy paste in A1, A2, and so on. So I can write A1, 0, A2, 1. I won't spend time writing that right here because it's just a matter of putting it down. What I would do is I'll just give you the final A3, 0, which is what I'm after. A1, 0, A2, 1, A3, 2 equals. So when you do this math, you get, that is, you figure out A1, 0, and so on. This is basically comes from the formula. You get C1, 0, minus S1, S1, 0, C1, 0, minus 1, 0, 0, 0, 0, minus S1, D3, C1, D3, D1 plus D2, 1. So this part is orientation. Let me write it this way. What I've written down is basically R300, T301, and so the orientation is R30, which is the 3 by 3 matrix. And the end effector position is S1, D3, and C1 is cosine theta 1, S1 is okay. So the last part is fairly simple. The first two parts